Hello. Thanks for joining us today. My name is Ravi Elluri. I work on Openshift automation and tooling.
I'm Sebastian Jug. I also work on tooling, mostly in Go, and I also focus on container runtime performance.
We are going to talk about automated Kubernetes scalability testing. So who are we? We are part of performance and scalability team at Red Hat, working primarily on Openshift. The wider performance and scalability team works on the entire Red Hat's products portfolio. I'm sure everyone over here might have played around with Kubernetes or OpenShift, which is an enterprise version of Kubernetes at some point of time. Quick show of hands, how many of you are running Kubernetes or OpenShift in production? That's a lot of people. When running OpenShift in production, one might have these questions in their mind. Does OpenShift support running applications at scale? If yes, then what are the cluster limits? How can we tune a cluster to get maximum performance? What are the challenges one might face when managing and running a large and dense cluster? We had similar questions in our mind. Over the next few slides, we are going to talk about how we built and used our automation pipeline and tooling to come up with the answers to these questions. Infrastructure is one of the key things we need to test any product at scale. With this motive, we built Scaleup. It's an initiative to operate Red Hat's products at their upper limits. The Scaleup consists of 350 plus nodes with 8,000 plus cores, which is a lot of resources, and we keep adding more and more physical nodes to this lab every year. The resources are all shared and are available on demand. Let's talk a bit about our cluster availability. We install a 2,000 node cluster once every OpenShift release and run various performance and scale tests on top of it. We maintain a 250 node cluster all the time to resolve customer issues, to design new tests for features added upstream, and for R&D work. We refresh this 250 nodes cluster with the latest and greatest OpenShift bits once every sprint. Our sprints are usually 3 weeks long, by the way. We recently completed a 2,000 node large-scale testing for OpenShift 3.11 running Kubernetes 1.11. I'll use this run as a reference to talk about how our automation pipeline and tooling works. This is how our automation pipeline looks like. The pipeline runs in stages, with each stage being an individual Jenkins job. So all the blocks over here are separate Jenkins jobs, and the pipeline controller is responsible for tying them up together. The pipeline is flexible enough to allow us to run a particular job instead of running all the stages by default. I'll talk about what each job does in detail over the coming slides. The first job in the pipeline is image provisioner. This job watches for new OpenShift code bits and builds AMIs and QCows with various packages, configurations, and container images baked into it. By doing this, it reduces the time taken by the installer to build out an OpenShift cluster, as the installer need not fetch any packages or container images over the network during the install time. This job has support to build images based on both RHEL and Atomic. Once the image provisioner is done building an image, it calls the image validator job. This job validates the image built by the image provisioner by installing an all-in-one node OpenShift cluster. So at this point, we can be sure that the image is good. The next components are pipeline controller and watcher. Given a properties file, which is where we define the parameters needed to build all the jobs in the pipeline, pipeline controller reads it over HTTP and then calls the respective jobs. The pipeline can run multiple jobs in parallel and supports running the jobs on both public and private clouds. We store all the job templates in a public GitHub repository. It's all open source, and it's in YAML, by the way, so it's easy to edit. And let's say we modify a particular job template or add a new job template to the GitHub repo. This is where the watcher component comes into the picture. The watcher component watches for these changes and creates or updates the jobs in Jenkins. Now that we have the image and properties files ready, we kick off the pipeline to build OpenStack. So why did we choose OpenStack? OpenStack provides the virtualization platform to scale out the OpenShift cluster to a higher node count. So by using virtual machines, we can make efficient use of the lab resources and also can run large-scale tests on a smaller hardware footprint. We use Triplo to deploy OpenStack. Triplo basically brings up the OpenStack under cloud, which manages the hardware and installs OpenStack over cloud. Over cloud is where we host all our OpenShift virtual machines. Triplo also installs say, SF cluster, which manages the storage for all these OpenStack virtual machines. This slide has the details about the hardware that we use for our 2,000 node scale test run. We got 84 machines allocated from Scaleup, and we converted that to a 2012 OpenShift cluster. Impressive, right? We use the same flavors as an AWS. The next stage in the pipeline, once the OpenStack cluster is up and running, is OpenShift. Everyone uses their own architecture to install and set up OpenShift. This is how we do it. There's a jump node or bastion host from where we control the install, manage the cluster, and run various performance and scale tests. There's a load balancer, which balances the requests to the masters. There's a DNS, which manages the cluster DNS. This job installs the bare minimum OpenShift cluster with 3 masters HCDs, 3 infra nodes, 3 storage nodes, 2 app nodes or worker nodes. I'll explain the reason for just installing a 11-node cluster in the coming slides. We call this 11-node cluster as core cluster. Most of the nodes in the core cluster uses NVMe pass-through, and that's because HCD running on the master nodes, Elasticsearch running on the infra nodes, Red Hat OpenShift Container Storage running on the storage nodes, needs high throughput and low latency for better performance. We also make sure none of the core nodes land on the same hypervisor for the cluster to be true HA and also for the performance and scale test results to be valid. The next job in the pipeline is to set up tooling. We built a bunch of open source tools, and Cluster Loader is one of the most extensively used tool by us. Given a YAML definition, Cluster Loader reads it and loads up the cluster with various objects. This is a sample Cluster Loader config. I'll explain what this config does. This config creates a cluster project, 0 namespace, and if the namespace already exists on the cluster, it deletes it and recreates it again, or else we can set ifexist to reuse the same namespace, and it loads up that namespace with 1,000 pause pods. The step size is set to 50 and the pause is set to 60 in the tuning sets, which means that the cluster loader will create 50 pods in the first iteration, waits for the pods to be up and running, and then creates the second set of 50 pods and goes on till it reaches the 1,000 pod count. This is just a simple example of what Cluster Loader can do. The things that Cluster Loader can do are unlimited. We can use the Cluster Loader to load up the cluster with a bunch of OpenShift templates to create thousands of namespaces with thousands of pods, secrets, routes, etc., etc.
We've also embedded Cluster Loader in the Atomic OpenShift test package. So those of you that have OpenShift already installed, you may or may not have this package installed, but yum install it and you're one step away from loading up your own cluster with whatever images or objects you like.
It's also available in upstream Kubernetes in case anyone wants to check it out. The next tool that we use extensively is PBench. It's a benchmarking and performance analysis framework. PBench has 3 subsystems. PBench Agent, which runs on all the OpenShift nodes on which we want to capture the performance data. PBench Agent provides various tools like SAR, IOStat, PithStat, and it's flexible enough to allow us to run our own tool. The next, PBench Agent also provides benchmark scripts like FIO, UPerf, and user benchmark. So using a PBench user benchmark, we can literally run any script and expect the agent running on the OpenShift nodes to collect the tool data. The next subcomponent is PBench Server. Once the agent is it's done running the benchmark, it tars up the results, ships it off to the server, where the results get unpacked, archived, and indexed. The last subsystem is the PBench Web Server. It's responsible for visualizing the data collected from the OpenShift nodes. I'll give a simple example to show how PBench works. Let's just enable PithStat tool on the OpenShift compute nodes and use PBench user benchmark to run the cluster loader config that we saw before. At the end of the run, we can see the memory usage of kubelet, CRI-O, Docker, or any other process running on the OpenShift node when the cluster loader is loading up the cluster. Powerful, right? The next stages in the pipeline are conformance tests and scale-up. This job runs Kubernetes end-to-end tests, and once the conformance is green, it scales up the cluster to a desired node count. The reason for running the conformance before scaling up the cluster to 2000 is that, let's say we find out that the cluster is bad. After scaling it up, then we'll have to tear it down and build it from scratch again, which takes a lot of time. So in order to avoid that, we build a core cluster, run conformance on top of it, and once the cluster looks sane, we scale it up to 2000. The OpenShift installer is Ansible based, so we usually set the number of folks to 50 for the task to run in parallel and speed up the scale-up time. The last stage in the pipeline is performance and scale tests. We design various tests to look at the performance of control plane, kubelet, networking, HA proxy, and storage. We also have a bunch of tests in the pipeline to validate and push the cluster limits. We repeat the same pipeline run with the latest and greatest OpenShift bits once every sprint to take a look at the performance regressions. The motive behind building the automation pipeline, tooling, and the scale lab is not just for our team. We are actively onboarding other teams to enable them to test their workloads at scale. This way, they need not have huge infrastructure. They need not install and maintain a large-scale cluster with the latest and greatest bits. They can reuse the tooling and automation that we built instead of maintaining their own. Adding a new workload to the pipeline is as simple as creating a PR with the right job template, and the watcher component will pick it up, create a Jenkins job, and adds it to the pipeline. Sebastian will take it from here.
Thanks, Ravi. So we have our cluster running, and then we need to run the tests. And let's take a look at what we found, some challenges that we faced. So this is just a quick list of some tests that I'll be covering. We have a good-sized team, so we have specialists in storage, networking, that take their respective components and make sure that OpenShift is actually compliant and optimized in each of these different test fields. And since we need to cover all the bases, not just the control plane, because of decisions that are made on behalf of Red Hat for the choices in HTTP, for the choices in storage, we'd have to make a lot more tests than just regular control plane tests. The first test, I guess you could say, is really just the scale up. So while you might not think it's a test per se, we do need to measure how long it takes to scale up, as well as each step to make sure that it's optimized, cached, and not duplicated. Obviously, if you're scaling to a small node count, install time's not that relevant, but when you have 2,000 nodes, it could take, if things go wrong, several days. So the NodeVertical is a most basic kubelet density focused test, and what it does is create the max pods across the compute nodes. And here you can see the kubelet as well as the container runtime system resources used by both of them across the versions, 3.9, 3.10, and 3.11. And this is one of the things that we optimize and strive to maintain is no performance regressions across versions. So it's the same test, adding a bunch of features, but you can see things don't get worse, at least. MasterVertical is the follow-up, more advanced version of NodeVertical. It's a more advanced cluster density test that doesn't just create pods. It's not just a theoretical best case scenario, but actually includes builds, secrets, routes, and all sorts of OpenShift objects outside of pods. The goal of the MasterVertical test is to have a more fully loaded environment that is more representative of real clusters. So here we have the control plane again, the API server, the controller, as well as etcd, with a exponentially increasing project count, and the projects contain the same amount of objects. So as you can see, as we move to double the project count, quadruple the project count, the control plane scales much better than linearly. So once again, scalability is something that we pay close attention to, as we want to make sure that you can run as many projects as humanly possible with your objects in them. The first decision that we make, I guess for you guys in OpenShift, is the choice of an Ingress HTTP router. What we use in OpenShift 3.11 is HA Proxy 1.8. So the major feature that we have in HA Proxy 1.8 is the router threading. And you can see the difference between OpenShift 3.10 and 3.11 in the different versions of HA Proxy. As we add in more concurrent connections, the throughput of the HA Proxy router scales quite nicely. Of course, this is also brought to you by another open source tool called MB that we've created specifically to be able to saturate these links. Networking is actually a relatively complicated topic with OpenShift on OpenStack because each of these products carries their own SDN. So this introduces a problem that we like to refer to, aka otherwise known as double encapsulation. Needless to say, that is not great for performance. We use, among other tools, we use uperf to benchmark node-to-node, service-to-service, and pod-to-pod throughput and latency for both TCP and UDP connections. The way we are working to get around the double encapsulation is a new product in OpenStack called Courier, which leverages the network abstraction of OpenStack Neutron to isolate the networks of the Kubernetes cluster. In this example, we have the default IP tables hybrid Neutron firewall driver compared to the newer, Open vSwitch firewall driver. At small node sizes, Open vSwitch produces better TCP throughput performance, but quickly falls off when the cluster gets larger. As for storage, our storage solution on OpenShift is Gluster, so otherwise known as Red Hat OpenShift Container Storage, formerly Container Native Storage, in case you're not keeping up with the names. Essentially, we run a pretty decent sized Postgres or MongoDB install on the cluster and then load it up with PBench. Specifically, in the improvements in 3.11, the Gluster block performance has increased substantially. Keeping with the theme, default installation of OpenShift does come with Prometheus pre-installed. The Prometheus stack is kubestate metrics, node exporter, and at very least, alerting. So 2 topics that we cover with Prometheus is the research and development of guidance as to capacity planning for Prometheus. We want to enable customers to collect large-scale metrics or, alternatively, maintain 15 days of retention. So the recommendation here is to have at least 1 terabyte of general purpose SSD storage. We also applied synthetic large-scale workloads that are based on Grafana queries, but applied synthetically, just to make sure that Prometheus can scale. And the next version of OpenShift, not 3.11, will have Prometheus 2.5, which does have some substantial both memory improvements as well as scalability improvements. So Configurator is not really another test, but it's another tool that we've written. One of the challenges that we're always striving to improve is the reality of the load test, right? We started, like I said, back with NodeVertical, and then MasterVertical, and now we have the config mirror. And what this enables us to do is essentially try to extract all the objects that we can from large-scale clusters, like OpenShift Online, and take out the user data, and then transfer them onto our Scaleup or other large piece of hardware. This enables us to debug performance issues that customers see as well on the field, because we don't often have access to their environments, and we certainly can't reproduce all of their configurations. So this is one of our newer tools that enable us to do so. So as with upstream, we've been closely tracking the cluster limits, and each of these fields, pods per node, pods per core, namespaces, we have tests specifically designed, most of them using Cluster Loader, as it's very it's trivially easy to generate whatever you want, namespaces or pods or any object, and load it up to hit these. But essentially every release, at very minimum, we track and verify the cluster limits. So higher limits. Recently, OpenShift, we started diverging a bit from upstream as our pods per namespace, they started seeing some issues, or Kubernetes started seeing some issues with pods per namespace. The API server started slowing down, bogging down, and we didn't see those same issues. So given everything we do, eventually, or we tried to make everything land upstream. Some things don't make it, but we're working with SIG Scalability, as I'm a member of them, to try to figure out why we have this difference right now. Oh, yeah. Is it possible to run 500 pods per node? So we currently support 250 pods per node. Theoretically, it is now possible to run 500 pods per node if your application does nothing. So Yes. Of course, getting there were some challenges. Even with DNS mask, it didn't like it, especially if you have a small cluster, you have like, what, 2 or 3 worker nodes, 500 pods per node, sure. 2,000 pods or 2,000 nodes later, it's not gonna work out. So it is possible to run 500 pods per node, but the issue becomes when you have real applications, real containers running on a node, it gets a lot more complicated. For starters, the first thing that happens is the container runtime seems to be the weakness at this point, preventing higher node counts, as the plague latency will keep increasing as you have more real applications, not just the control plane applications. The plague latency, which is a good indicator of health for the container runtime, will keep increasing over time, and eventually the nodes will become not ready, and things just escalate from there. The scheduler will say, we just lost a node, we need to reschedule 500 pods or whatever it might be, and there goes your cluster. Tuning. So we like to take a layered approach to tuning to address performance issues. As best as we can, we try to optimize for performance at the lowest level, which is the code level. We work very closely with engineering teams at Red Hat, obviously, and all of our work does eventually, for the most part, get to upstream. Next, we try to take tuning on. So if you're running RHEL, you definitely, out of the box, get the tuned daemon. Essentially, what this is a daemon that runs on your system and automatically applies our best practices, our best tuning knobs to your nodes based on whatever profile you select. So if you have a storage node, you can select for throughput or I/O, not both like someone was asking for earlier at the booth. If you have an OpenShift master node, it's all tuned out of the box, so you just need to select it, it's set at boot, and you don't have to worry about it. Of course, you can take this further if you have special needs. For example, the API server has QPS and burst rates. Out of the box, we set this as same defaults for any size cluster, but if you have these monster iron rigs with 96 cores and 4 different sockets, then we can do a little better. If you up the QPS and burst rates, the scalability does drastically increase, but at some cost. So every major release we update our scaling and performance guide, and this guide covers all the topics that we discussed, everything from the installation tunables, the API server overrides that I just discussed, the kubelet configs to increase the density, the networking and routing optimization, as well as newer features that we're working with and adding to Kubernetes to support running your actual workload and tuning your workload to make sure that you get the best performance for your applications, such as a CPU manager, huge pages, and now GPUs. So, like everything we do, our code is all open source and upstream, good, bad, or ugly, it's here. So if you want to take a look, run it, kick the tires a bit, or fork it and contribute, it's up to you guys. What's next, Ravi?
We are planning to test operators at scale, which is the buzzword for this conference, by the way. And we are working on onboarding more and more teams into our pipeline to take advantage of the automation infrastructure and tooling that we built. And we'll continue to push towards higher cluster limits. And we are also working on adding support to the pipeline to run in various public clouds. It does have support to run the scale tests in any cloud since it's all containerized. It's the install phase that you're working on. Thank you. Next slide. So, before we jump on to the Q&A session, I just have one last thing to say. We are hiring the famous last words. Please feel free to reach out to us to know more about the interesting things we are working at Red Hat. Thank you. Any questions? Yeah.
As far as I understood, you guys are running with all the nodes and everything on OpenStack on your lab.
Yeah.
So is the lab shared, or do you guys just use it for your pipeline?
No, it's all, the lab resources are all shared. Like the lab is like huge. Like we just get like some nodes allocated once every OpenShift release. We take them, install OpenStack on top of it, and then run our pipeline, and then we just give away the machines once we are done.
So,
But do you guys ensure the same performance with VMs?
We use the same VM sizes, like same machines, with like same memory resources, CPUs, and everything all the time, so that like we can get a run-to-run comparison between the previous runs.
So there's no tuning for burst?
You mean on the OpenShift cluster? Yeah, we manually tune the QPS and burst rates for a cluster. So one time when we are running a test which created 10,000 namespaces with like a lot of objects, secrets, routes, and all that, like the API server got overloaded, and then we had to like tune the QPS and burst rates, like double them up, quadruple them up, to like get the cluster back to running state. So this didn't happen on the 250 node cluster, which we usually maintain every sprint, and that's because there are just 250 nodes hitting API server instead of 2,000 nodes. So depending on the node size, like we do some tunings on the cluster. Yeah.
Yep.
Did you stress test with any stateful applications on your cluster? Like, I know when you're doing, basically you're using the same images to run as pods, right? Like 20,000 nodes. There might not be an approximate distribution of the workload that the customer might enforce in their application, right?
Yeah, so we have a number of different tests, right? So in different stages of reality, we do try to make things as real as possible, and we do have, I guess, like whatever database specific tests and all sorts of different tests that would have state as well. Sorry, go ahead, yeah.
I don't see you use Kubernetes for is there a particular reason?
Yeah, so that's more of an upstream test, and it doesn't work with all the OpenShift objects. So right now, we're moving in upstream as well. I believe we're moving away from kubemark. We're rewriting the upstream cluster loader to add the additional features. Also, I'm pretty sure kubemark is the hollow pod one. It doesn't run on real like pods and nodes. It just creates like virtual ones. So all of these tests are on real hardware using real nodes and all that. So we're really trying to strive for reality, and that's where we come with the tunings that Ravi mentioned is just actual issues that we encounter.
Yep.
Yep. Yeah, so since that's not GA, we can't discuss that at this point, but we might, definitely maybe.
Yeah, we'll have the numbers soon. Yeah.
So, how did you go about deciding to use PBench? And was there any, did you find other tools out there that you could use? Or did you see that PBench was better or was it certain things?
So I think that started with we have a large performance and scalability group that doesn't just work on OpenShift specifically. It works across all RHEL products. So we needed something that was pluggable and modular to work with all the basic tools, because I'm sure you guys are familiar with that chart of Linux performance measurement tools. So we needed something that could capture anything and everything and could be easily extensible. And so that's why we wrote PBench, was just, we didn't want to have some sort of like tailor-made stuff. It's pretty easy to just add a new tool to PBench and capture it and record it and compare it. So it really just came down to extensibility and standard tooling. No problem.
Yeah, it's quite flexible. Like we can literally like create a script right now which collects OC get nodes, and then and we can add it to PBench, and then it will collect OC get nodes every 3 seconds or 10 seconds depending on the interval while your test is running. So we can extend it instead of like depending on the other tools. Yeah.
Sham, what's up? Yeah, of course, of course. Yeah, so SIG scalability, just trying to,
To complete my question,
sorry, go ahead.
I mean, you probably know the case that right now every release there are some major scalability regressions and we like kind of talk on them, and we are very limited manpower, and SIG scalability is kind of like very niche effort right now with very few people working on it. And given that you have so much already that's built around stuff, if you catch some regression, maybe you can contribute towards the upstream Kubernetes data that are possible.
I would say we don't have plans, but that's something that I do care more about, so we should talk about why that is, maybe offline or whatever, not on video.
Yeah, we do report things to SIG scalability. So recently, we ran a test to see if we can increase the pods per namespace more than like, it's 3,000 right now, so upstream lowered the limit. So we thought like, why not create a test and then try to see like if we can increase the number of pods per namespace. So we found out that it can be increased, so we reported the results back to SIG scalability. So our plan is basically to get the change upstream first and then basically get that into OpenShift instead of just modifying it in the OpenShift level.
Yes, that's some really valuable
Yeah.
information that we would like to make it common knowledge that everyone.
Yeah, we haven't changed any of our limits, so we are planning to get it merged upstream and then get it down to OpenShift.
All right, thank you very much.